All right. So Kleen's theorem is the theorem that says a set is regular if and only if it is recognized by a finite automaton, right? This is what we already said. We defined regular sets in the previous video, and we said they are the sets that can be recognized by finite automata. So this theorem is just saying that, that's all. But I want to make this short video sort of explaining the method of proof used here, because it's a great application of a proof by induction. So we're going to start with a base case, right? Let me flip back here to remind you the definition of a regular set is a recursive definition. There's a base case saying these simple sets are regular, and then there's this recursive rule which says if you have two regular sets, then you can produce other sets which will be regular as well. What we need to do to prove that those sets can be recognized by finite automata is to show that each base case can be recognized by a finite automaton, and then that if you are combining together using union or concatenation or making a clean closure of something, that can also be done with a finite automaton. So that's I'm going to sort of do part of one direction of this if and only if statement. I'm not going to show you the whole thing, but I want to get you the gist of it because I think it's pretty cool and really lets us wrap our heads around the sort of theory of this theorem. So first of all, the empty set is our first base case element that we say is regular. So to show that that can be recognized by a finite automaton, we just need to build an automaton to recognize that. Thankfully, that's pretty easy to do. We only need one state, state 0. It's our starting state. And it's not going to be an accepting state. So that way we don't accept anything at all. Whatever inputs are received, say we receive input X, we'll just loop on that state and stay where we are. That's it. It is a machine that recognizes nothing. And that loop there with input character X, that is for all X in your input alphabet. Okay, so I'm going to be using X as like an arbitrary element of I in most cases. So there we have a machine that shows that the empty set is recognized. It's possible. Now, the set containing lambda, you might think, well, isn't it the same? Not quite, because what we want is to recognize the empty string but nothing else. So we do have to have one accepting state. Our initial state at 0 needs to be accepting in this case in order to recognize lambda. But we don't want to recognize any other string, just that one. So if we receive any other element of the alphabet, then we need to go to a new state, which is a pit of despair where it's not recognized. So if you receive anything, go to this state 1, and if you receive anything further, stay in state 1. This is, again, for all X in I. So that's our little simple machine, which is going to recognize just lambda. And finally, we need to show that you can build a machine that's going to recognize a particular element A that's specified, but nothing else, like the singleton string, length 1 string A. And that is recognized by the following machine. By the way, I should have said this, but you should pause and try to do this on your own, actually, before I go through it. So now that I've shown you the first two, maybe you could pause and try to do this one. We'll go through it here. I don't want my starting state to be accepting, because I specifically don't want to recognize lambda. I just want to recognize A. So if I receive the A that I want, then I'm going to go to a state which is an accepting state. Just that. If I receive anything else besides A, I'm going to call that X, and this is going to be for all X in the alphabet, which is not equal to A. So here I'm saying specifically anything except for A. That would take me to some other state, which is not accepting, where we can loop. And if I receive A followed by anything other than A, I also need to go over here. But even if I receive like AA, like 2 A's in a row, I don't want that. and any further A's I don't want either. So so if I've got A and then I've got X, which is anything other than A, then I would make this machine where A by itself is accepted, but anything else, whether it be X's or further A's, are not. So there we go. So those are the three base cases showing that those machines can be built. And then the proof would proceed by induction to assume machines exist to recognize sets A and B. So we call those machines M subscript A and M subscript B. And then assuming that's like your sort of inductive assumption, what you'd want to do is then show that it's possible to take those machines, MA and MB, and combine them together in some way to create new machines that are going to accept the concatenation A-B, or the union A-union B, or the clean closure of one of them. And that is done in the textbook using something called non-deterministic finite state automata. So I want to show you a couple of things from the book here. So a non-deterministic machine, first of all, is a machine that doesn't have to follow the same rules that a deterministic machine does. For example, it doesn't have to include all possible. It doesn't have to give you a rule for every possible input combination. Like there could be states and certain inputs that don't produce any output. Okay, so you can basically have blanks in your state table, or you can have the machine do multiple things at once. It can say when you receive state 0, when you're in state 0, if you receive a 0, you can go to more than one place, like loop, and also transition to a different state. In real life, this is impossible, right? Because in real life, a machine can be in only one state at a time, unless you're keeping track of numerous different states, which actually, so it technically is possible. It would just be a bit strange. I think of it like, I kind of like to think of it like alternate realities, where there are two possible results of this input. One is to transition to this first state, and the other is to transition to another state. And there could be more than two, 3 or 4 or 5, or as many finite number as you want. So you can be in multiple states at once, and then that means that every time that you receive an input, you're transitioning from all of the states you're in to all of the states you would be in according to that next input you received. So it's this branching, you can imagine as this branching alternate realities where you end up in lots of different states at once. So at any given time, you are in a set of states, not just a single one. And it's wild. But complicated as it is, it doesn't actually give you any more functionality than a deterministic machine, which is interesting. It seems like with like relaxing the rules and giving you a bunch of other capabilities, you might be able to like do more things, like recognize more languages. But I think it was Kleene himself actually proved this theorem, which is to say that if a language L is recognized by a non-deterministic finite state automaton, then that language is also recognized by some deterministic finite state automaton. Now, the benefit of a non-deterministic machine is that it's possible to make it much simpler, like with fewer states and a simpler description. But anything you can do with a non-deterministic machine, you can also do with a deterministic machine. It might just be more complicated with lots and lots and lots of states. So that's the distinction between non-deterministic and deterministic. Doesn't give you any more capabilities, it just can be simpler. And so for that reason, Kleene used non-deterministic machines in his proof of his theorem. So I just want to come back over to this page. This is the inductive part of the proof, where we're making the assumption that we have machines that recognize A and B. This is a diagram that shows how you can combine those machines together to make a new machine that recognizes the concatenation AB. This is the diagram of the combined machine to recognize the union, and this is a diagram of a machine that would recognize the clean closure. So that would complete that portion of the proof, showing by induction that if you can do it with A and B, then you could do it with all of these different combinations using operations. And that shows that all of those things are recognizable by a machine. So that's kind of all I wanted to show you for Kleen's theorem. It is a pretty big result in the study of a study of finite state machines and that particular type of computation model. But as I've said, it's still limited because it can't compute anything. So for that, you would need to take this idea of a finite state machine and build on it and create what's called a Turing machine. So Alan Turing, also in the 50s, expanded on Kleen's ideas and did a bunch of really cool theoretical computation models that essentially laid the groundwork for modern computer science as a field. Yeah, that's about it. This pretty much wraps up the semester, actually. Kleen's theorem is the last thing I wanted to tell you about. Unless there was anything else in my notes. Let me just double check my notes. Oh, no, there is one. Oh, yeah, that's right. Okay, I'm going to make one more video to show you an example of a set which is not regular, and then I think that'll be it. Here we go.